practice problem. So an example of how this can be used, and we're also going to be dealing with vector notation here. This will be practice for gravitational force. Let's see. Looks like, it is coming up. So here's this problem. We've got three 0.3 kilogram billiard balls. So we know the masses are all the same and they're 0.300 kg, are placed on a table at the corners of a right triangle as shown. We've got a little picture there. Let's see. We've got mass 1, which is the cue ball. We've got mass 2 above it, in yellow in this picture. That is a distance A, and then we have a distance B off to the side, or mass 3, a purple ball. And it tells us inside of here what A, B, and C are. Now, as it turns out in this problem, since we aren't asked to find the force between mass 2 and mass 3, or mass 3 and mass 2, we're not actually going to need C. We'll just need A and B. But let's get all three of these written down. A is 0.400 meters, so this is a taller triangle than it is wide. B is 0.300 meters. This is a 3, 4, 5 right triangle, so it would be 0.500 meters alongside C. We want to calculate the gravitational force on the cue. Now you'll notice we do have two objects here. Mass 2 and mass 3 each acting on the cue ball. So this is actually going to be a sum of forces problem. We have two forces that will get added together. We're going to find each of them individually. All right. So let's find the force due to 2 acting on 1, and separately the force due to 3 acting on 1. Since this has been put in a Cartesian sort of system, we can just think about x, y, and z, so we don't have to think about r hat here. We can think about I hat, j hat, k hat. All right, so first one, mass 2 and mass 1 acting on each other. We're going to have big G m squared because they're all the same mass. m1 equals m2 equals m3. Then it's going to be divided by a distance that is a squared, and this is along the positive j hat direction acting on the cue ball. All right, so if we put numbers in there, 6.674 times 10 to the minus 11 Newton meters squared per kilogram squared, 0.300 kilograms, oops, put the parenthesis in the wrong spot, kilograms, whole thing squared, all over 0.400 meters squared. Quick check, kilograms will cancel here, meters squared will cancel there. We're just going to get units of newtons. This will be in the j hat direction, and we get 6.674 times 10 to the minus 11 times 0.3 squared divided by 0.4 squared, 3.754, which we'll just round to 3 digits of precision because all of our numbers were 3 digits of precision, times 10 to the minus 11 newtons in the j hat direction. We'll do the same thing for 3 and 1, 3 in the cue ball over here. Gm squared over, this will be b squared. The direction is in the positive I hat direction now. I'll go ahead and put the numbers in one more time, although putting the numbers in can get a bit tiresome once you've figured out the equation. 0.300 kg squared all over 0.300 meters squared. So as luck would have it, I don't need the calculator for this one because 0.3 and 0.3 will actually cancel with each other. The meters will end up canceling because we've got squared top and bottom. The kilograms will cancel because we've got kilograms top and bottom. 0.3 squared ends up canceling. We get 6.67 times 10 to the minus 11 newtons in the I hat direction, meaning our final result on 1 is going to look like 6.67 times 10 to the minus 11 I hat plus 3.75 times 10 to the minus 11 j hat newtons. Now, I want to talk about this for a moment. This is one form you can put a vector in. There's I hat, j hat, k hat notation, unit vector notation. Then there's magnitude and direction notation. How would this look if we wanted the magnitude and the direction? Well, I'll remind you that the magnitude is the square root of the x component squared plus the y component squared, and take the square root. And the direction is the inverse tangent of the y component over the x component. And this is general for all vectors. There is a warning I want to make here. Theta will be between pi over 2 and minus pi over 2, or if you prefer 90 degrees and minus 90 degrees. If looking at your drawing you know that the actual vector direction is not in those quadrants, which would be quadrant 1 and quadrant 4, then you have to, if not there, you have to add pi, or 180 degrees. So be aware of that when you're using inverse tangent. Your calculator is not very bright about it, so you're reliant on your own brain to figure out, am I in the right quadrant for the result? All right, in this case, it actually comes out in quadrant 1, so this is pretty trivial. So if we put the numbers in, we'll take that one and square it, and then we'll add 6.67 times 10 to the minus 11 and square that. Take the square root, we get a magnitude of 7.66 times 10 to the minus 11 newtons, and we get a direction. Let me make sure I get this right, 3.75. We can drop the 10 to the minus 11 because it will cancel, divided by 6.67, and then inverse tangent, and we'll find out what mode I'm in. I am in degree mode. All right, so 29.3 degrees, or if you prefer, you can multiply that by pi and divide by 180 and get it in your radian mode. All right, so 7.66 times 10 to the minus 11 at 29.3 degrees would be a valid answer, as would saying it as 7.66 times 10 to the minus 11 newtons at 0.512 radians. Or you can state it in unit form, 6.67 times 10 to the minus 11 I hat plus 3.75 times 10 to the minus 11 j hat newtons. There will be some problems where I ask you specifically for either magnitude and direction or component form. You must render it into the correct form when that happens, so if you need a review of vectors, that is also at the bottom of the section. All right, that's going to be it for this one. I'll see you in the next video.